I'll get started. There's a bit of a, I guess, mistake maybe doing it during a 374 and a 473 exam, turns out, but whatever. So yeah, so today I'll give you a natural deduction and essentially just a little bit of like logic and proof theory stuff. So the stuff that you need to know sort of to this motivate this construction or like this proof system that we're going to be building. So yeah, I will be introducing pitch style natural deduction and intuitionistic propositional logic, but I'm also planning on having this be like reasonably interactive. So it'd be helpful if you guys do interact, but if you don't, I mean, we can always move forward. And yeah, there are exercises at the end, sort of. So if we get to them, we get to them, and we can do some proofs on the board. And if we don't get to them, well, you guys can just download the slides and look at them later. But yeah, so moving on, without further ado, let's talk about logic. So I wanted to introduce some notions from logic. I'm probably not like, these are kind of not the most relevant because I'm not really going to be talking about them, but they're just here in case. These are some definitions and stuff that you're going to see show up if you look into proof theory. And like, I'm not really going to use them, but some logician or some philosopher is going to get mad at me if I don't show them. I mean, I have a programming languages background, so this talk is going to be pretty programming languages coded rather than like philosophy or logic coded. But yeah, so first of all, I'm going to define a formula as like a string in a formal language. So if you take a 374, you know what a string is. You have some sort of finite alphabet, and when a finite sequence of characters from this alphabet, we're going to call it string. We're going to say in a formal language, we have some sort of grammar or some sort of rules for generating, like basically saying what sort of languages are valid in this language and what sort of sentences are valid in this language. And that's going to say, we're going to say a formula are strings of that form. So if I have, let's say, a context-free grammar to generate my language, any like strings that actually show up in that language are going to be formula, and any like random garbled mess of characters from the alphabet, those are strings, but they're not actually going to be part of our language. A sentence then is going to be defined as a formula with no free variables. So there's a notion of like bound variables and free variables. It's not very important to the content of this talk, but essentially if the variable has like been assigned to something, let's say for all x, px, x we're going to say is bound, but if I have like for all x, px, j, x is bound and j is free. And then a statement is going to be a sentence with a definite truth value. So I'm not going to require sentences to have truth values. They can be true, false, but they can also just like not have truth values whatsoever. But yeah, moving on. An argument then I'm going to define as a sequence of statements. So we're going to say, we're going to have to define a notion of validity for arguments and a notion of soundness. I'm going to say an argument is valid if it deductively follows, in the sense that you can have this sense here where every sentence follows deductively from previous sentences. You can also have the sense where basically, is it true that in every instance where my premises are true, my conclusion is entailed? And I'm going to call it sound if the argument is both valid and its premises hold. So yeah. Moving on to logic or propositional / first order logic / propositional calculus, or whatever you want to call it. Propositional logic is like the most simple form of symbolic logic in any sense. You've probably seen this in like 173 or something. It's the P's and Q's thing, the P's, Q's, or whatever. We're going to, like the language that we're going to use in propositional logic is inductively defined from atomic propositions and these logical connectives. Each of these logical connectives is a so-called truth function. So sometimes you'll hear stuff, but you'll hear classical propositional logic called truth functional logic. It's called that because truth functions are functions that take truth values to truth values. So a connective like and is a truth function in the sense that the statement P and Q only depends on like its entire truth value depends only on the truth values of the substatements P and Q. So I'm going to go again, since I'm a programming language person, I'm going to want to define a grammar for like the language of propositional logic. Do you guys have any ideas for how we're going to define this grammar? So I'm going to get us started. I'm going to say we're going to have formula. So formula, and I'm going to use a script. I'm going to use script capital letters for like symbols in our meta language. I'm going to say formula, and I want to go inductively define what a formula can be. So what do you guys think our first case should be? in this grammar. Right, so what is our base case for a sentence in propositional logic? Well, so, all right, so if you look over here at the slides, we have atomic propositions and truth functions. What do you think should be the smallest thing? Atomic proposition. Yep, an atomic proposition. So I'm going to use like normal uppercase letters for propositions, atomic propositions. So these are going to be like A, B, C, D, P, Q, whatever. That's the kinds of stuff that you see in 173. We're going to use P for propositions. And then what else do we need? All right, so what are our logical connectives now? How do we join? How do we make bigger propositions from smaller ones? Yep. Yep. So we're going to have, I'm going to allow a formula A or B. I'm going to allow formulas A and B. Any other ones? No. Not yet. So I got a unary truth function, not. Anything else? Implication. So I'm going to say we're going to have A implies B. And then I'm going to add two special symbols, top and bottom. Top is going to symbolize true. It looks like a T, and bottom is going to symbolize, well, bottom is going to be false. It's called bottom because Boolean algebras are something called a upper semi-lattice or whatever you want to call it. But this is from order theory, but it's just a symbol that we end up using. So if you scroll to the next one, you're going to see here is the grammar that we constructed. We're going to start with convince yourself this is exactly the same as this. Maybe this is reordered slightly, but this is the grammar we're going to be working with for propositional or zeroth order logic. Notably, it's missing things. If you've taken 173, like in math class, you're going to think, well, what about quantifiers? What if I want to quantify over objects? Well, that brings us to the next order of logic, which is first order logic, or the predicate calculus, or whatever you want to call it. First order logic extends propositional logic by adding the ability to quantify over first order individuals, as well as have predicates that act on these individuals. So this has a little bit of a model, like to formally define this, you're going to need to know a little bit of model theory. This is not a model theory talk, so I'm not going to like spend a lot of time on this, but essentially in any model for a theory, we're going to have a domain from which these first order objects live. So like in the theory of number theory, which is the theory of natural numbers, we're going to have natural numbers as domain objects, first order objects. In the theory of groups, it's going to be groups. In the theory of sets, it's going to be sets. You can kind of get an idea of what this first order object is referring to. And we're going to have predicates where they're going to be things like x is prime, right? The meaning of the sentence x is prime, well, it's not only dependent on the first order individual, I gave it as X, but it also depends on like the particular interpretation of this predicate in that model. Again, this is model theory stuff. It's not really relevant to the point of the talk, but you're going to see words like this appear if you ever try to look into logic. So it's a little bit of exposure for now. I guess that's not good. So we have this logic for propositional logic. We have this grammar for like the formal language of propositional logic. How do you think we want to go about extending this grammar to make first order logic? So remember, what we added are predicates and quantification. So how would we modify this grammar? Any thoughts?
For all x, px.
Yep, exactly. So we're going to go add a new case for all x, px, let's say. What else?
That also exists.
Yeah, exists. And then I'm going to say, instead of atomic propositions here, we're going to actually work with predicates. So these are going to say are defined in terms of, there's going to be maybe some use of like some sort of use of terms. So it's going to be a predicate in terms of these kinds of things, tau. I'm going to tell you what tau are. Tau, I'm going to say are terms, and I'm going to just define them as variables. I'm going to use lowercase Latin alphabet letters for variables. The reason I define it this way, where terms are independent, is because I don't want an individual term to be a formula in this in the language, right? I don't want to be able to say something like 5. What does that mean in number theory? Nothing, right? I want to be able to say sentences about things. I want to have terms be their own non-terminal in our grammar. And then also, this is kind of hiding a little bit, but if you look at actual grammars for first order logic, you'll see things like constants and functions as well as terms. Again, not relevant to this talk, so I'm not going to go introduce them, but yeah, just don't be surprised if they show up. This is convince yourself that this is the grammar that we have here. Yeah, but with that out of the way, this might be something you haven't seen before, and is a little more philosophical in nature. But there's sort of two main schools of thought for what logic should be, and that sort of revolves around what philosophical beliefs you have about the meaning of truth. So how do you define truth? You have one class which takes a position called realism and truth values, where they believe that truth is an objectively real thing. Every statement must, or every sentence must have like some truth value to it, even if we cannot prove that it is the case. So something like the Riemann hypothesis, the Goldbach conjecture, P equals NP, these people, they assert that, well, there is some truth. Either P equals NP is true or P is not equal to NP. We just don't know what it is and we can't prove it. But they assert that this truth really exists. And this is the position we call classical logic. It is the position that is by a large margin the most popular because it allows us to do a lot of things. But starting from like around the, I think, early 1900s, Brouwer, if I don't know Swedish, something along those lines, mathematician, came up with this concept of, well, his opinion of truth is akin to knowledge, right? So Robert Harper at Carnegie Mellon, he has this thing which he likes to say tongue in cheek, which is that intuitionistic logic is essentially the logic for humans in the sense that it's like a kind of communication. I don't believe that something is true unless you can show me that it's true. So unless you can provide me a proof, I will not say that it's true, nor will I say that it's false. So we don't admit the logic excluded middle. We rather say that, well, unless you can give me an algorithm for constructing a proof or a witness of the truth value of this proposition, I'm not going to take it to be true or false. So of course, that is like kind of a whack job take because it doesn't allow us to do things, like a lot of things, like a lot of modern analysis we can't really do with intuitionistic logic. But computer scientists tend to like it because it gives us like a sort of computational semantics for our proofs, right? You can sort of think of proofs as programs in the sense where they're sort of algorithms for constructing like examples that witness, right? If I say something like 5 is prime, a proof of that is some algorithm that tells me 5 is a prime number versus maybe someone in classical logic will just pull something out of their hat and they'll say, well, we have some prime. There is a number root 2. How do you get this number root 2? I'm not telling you. I'm just going to say it exists. But yeah, with that out of the way, that's the logic background. Any questions before we get started on talking about proof theory? Okay. So what is proof theory? Well, proof theory is the study of formal proofs. In particular, we take proofs to be mathematical objects like any other. And because of that, we get a sort of algebra on proofs. We get the ability to sort of like compose proofs together and talk about equality of proofs. We won't be talking about that part of proof theory today. We'll be more talking about something called structural proof theory, which focuses more on like the structure of proofs, what is a proof. But yeah, historically, the motivation for proof theory was philosophers and mathematicians like Frege, Hilbert, and Russell. They wanted to sort of mechanize mathematics. They wanted to take math and turn it into a syntax game. So they claim that we can sort of argue that math is real or a priori like analytic by having this sort of way to do, if we can reduce math to logic and we accept logic as a priori, then we can sort of accept math as a priori. But that failed. Everyone knows, well, maybe not everyone, but Gödel proved that doing so is not going to work. And it kind of hurt this field a little bit, the logicists, but proof theory still has many useful applications in computer science, so we still talk about it to this day. In particular, we're focusing on structural proof theory, which studies proof systems and like their strengths. So here are some questions that you might want to answer in proof theory. Again, this is in contrast to model theory. Proof theory is a syntactical thing. We focus mainly on the syntax of proofs. Well, in model theory, we focus on the semantics of sentences. So stuff like when is 5, in what models is the sentence 5 is prime true? Something like that would be model theory. In proof theory, we care only about syntax. So In particular, we're going to talk about proof calculi or proof systems. Here's a definition. A proof system P for a formal language L, so keep in mind we need to have a formal language, is going to consist of axioms and axiom schemata. So axiom schemata you can sort of think of as templates for generating axioms. So an example would be something like induction, right? You have induction needs to take a proposition and then it turns that proposition into an axiom. So along the lines of if I can prove P0 and I can prove for all n P of n implies P successor of n, for all natural numbers n Pn is true. Induction acts on these predicates. It doesn't actually act on like first order objects by themselves. But yeah, then we also have rules of inference. So this is like, how do you progress? What can we do with these sentences that we have? How do we apply, how do we move forward in our argument? So I'm going to introduce some notation. I'm going to say gamma derives phi if the formula phi is provable in P. So P is our proof system from a set of assumptions gamma. So yeah, you're going to see this syntax a lot. This single turn style very notably is very different from the double turn style, which is some sort of semantic entailment, but you'll see both symbols show up pretty often if you do logic. Some examples of proof systems include the Hilbert system. It's like a kind of system developed by Hilbert, but the main idea is we take we take a large set of axioms and a very small set of inference rules, typically only like modus ponens. So that's like saying if I have P implies Q and I have P, then I can claim Q. You take that as your only inference rule, and then you have a massive set of axioms, which tells you, okay, I can sort of keep trying to pull in axioms and then try to use modus ponens to massage my thing into what I want it to look like. I mean, it works. It's very nice computationally. The only problem is the proofs are very big and they're kind of hard to follow. You also have natural deduction, which was discovered independently by, I think, Jastrzewski and Jensen. And the idea with natural deduction is we want to capture a more natural style of proof writing, which whatever natural means, right? The idea is they want to capture the notion of how mathematicians actually think. So in natural deduction systems, we typically take few or no axioms and like a large set of natural inference rules that we can use to sort of move forward. There's two main families of natural deduction proofs, Fitch style and Gensen style. The Fitch style is like an evolution of the Jastrzewski style, which look more similar to the Hilbert systems and like kind of similar to programs. So we're going to go introduce Fitch style notation. But Gensen style notations, the Gensen style proofs you'll see a lot in programming language theory, where essentially instead of going linearly, we do our proofs as trees. And you'll see stuff like this in CS421 about like proving semantics of programming languages. Yeah, but moving on. There are a lot of applications to proof theory, although it might not seem like it. In particular, here are a couple applications that I find particularly interesting. You have formal verification of software systems, right? Everyone hates writing unit tests. What if we can instead prove that our code works, like our code never fails? We also have proof automation in mathematics, which is like if you ever use a proof assistant like Lean, Coq, Agda, Idris, Hall Light, whatever. If you've ever used one of these like proof into like automated theorem provers, their type theories that they're based off of use proof calculi as like their inspiration. Logic programming is another application. If you've heard of the language Prolog, it's a language where essentially the way you model things are you have like a set of sentences that you say are true, and you basically your computation is doing logical deductions. And then you also have defining semantics for languages. So not just in programming languages, linguists are actually particularly interested by these kinds of proof theoretic ideas in actually sort of trying to define semantics for natural language grammars. But yeah, now that's done. We can introduce this this system of natural deduction that I want to introduce called Fitch style natural deduction. We're going to first introduce it for intuitionistic propositional logic. That's propositional logic where we don't admit the law of excluded middle. And we're going to slowly upgrade it. So once we finish the rules for for propositional logic, we're going to upgrade it to first order logic, add quantifiers, and then we're going to go upgrade it to classical logic by adding axioms. But yeah, so again, the motivation for natural deduction
well, let's think about how do we know, what do we know about writing logic proofs right now? Well, truth tables, they don't really give us, like, anyone who's done truth tables in 173 knows they're not really fun to do. They get very big. When your sentence gets complex, it's intractable to kind of prove whether your argument's actually valid. They don't give us any insight into the argument, and they don't really tell us whether, well, they don't actually work in intuitionistic systems, because a truth table always assumes like this sort of bivalence property. We'd say, okay, take P to be true and Q to be false, take P to be false and Q to be true. It only like ever assumes, okay, we know we have a definite truth value. You have also like maybe try doing stuff like substituting logical equivalences. Oh, I know De Morgan's laws. I'm going to go substitute that in. Oh, I know P implies Q is the same as not P or Q. So I'm going to try substituting that in. Everyone knows those proofs are hard to come up with, hard to verify, and also hide implicit assumptions. You might not know, but De Morgan's laws only works in one direction if you're working in an intuitionistic system. Well, like contrapositive just does not work at all in an intuitionistic system. So to make these more explicit, we have natural deduction systems, which typically try to focus on reasoning. Well, again, I said focus on reasoning in a natural way. Here's a quote from Frank Fenning in his lecture notes on constructive logic. And yeah, so the main motivation is to devise rules that model mathematical reasoning as directly as possible, although clearly in much more detail than in a typical mathematical argument. So again, I'm going to remind us, this is our language for propositional logic. And I'm not going to introduce any axioms for now, because the axioms we're going to go introduce later when we talk about classical logic. So I'm going to go immediately into the inference rules. So remember, the three things we need for a proof system are language, axioms, and inference rules. So the first inference rule I want to introduce is reiteration. So what does this mean? Well, this means that if on line M of my proof, I was able to prove that the formula A is true, then I can sort of reiterate it, right? If I prove that 5 is prime, I can say 5 is prime again later on in my proof. Nothing's stopping me from doing that. That makes sense, right? But the way you read this notation is essentially line M, I proved A is true. Line N, I'm saying A is true again, and my reason is reiteration on line N. The next one, conjunction. So this is our first logical connective. I guess I'm gonna have you guys help me with this one. What do you think? What kind of information do you think we need in order to say that the sentence A and B is true? So this is sort of, we want to introduce the and symbol to our proof. What sort of information do we want to have?
It's true, and B is true.
Exactly. So we want to have, if we can show that A is true on line N, and we can show that B is true on line N, then we can use this rule called the and introduction rule and say, therefore, A and B must be true, right? It's kind of natural so far, I guess. What can we do with A and B? So if we knew that A and B is true, and we want to get rid of this and, what can we say? Well, clearly we can say A is true, right? And also clearly we can say that B is true. So that gives us the elimination rules for conjunction. So if on line M we manage to prove that A and B is true, then we can sort of eliminate the and, get rid of the and say instead, okay, well, forget about the and B part. We're going to just say A is true. So yeah, these are the rules. Memorize them. Our next connective is going to be implication. So this one I'm going to go through because it introduces some notation, but essentially the idea is you can read this as sort of starting a subproof. So like this is our actual main proof. We can, if we want to prove that A implies B, well, how do you do that in like a normal math proof? You say let A be arbitrary, blah, 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 and then, okay, therefore B, right? You sort of say, I assume that A is true, and then I somehow show that B follows. You do the same thing in a natural deduction system. You do what's called open a subproof, and you make an assumption. You say, I assume A is true, but I can somehow get that B is true. Then at the end of that all, I can close my subproof and say, well, this proof is evidence for A implies B being true. So the elimination rule for implication is just modus ponens. What you guys might be used to. If I have the statement A implies B being true, and I have managed to prove that A is true, then I can sort of get rid of this implication. I can instead go through and get the conclusion B is true. So yeah, hopefully relatively straightforward for now. Our next one is disjunction, or I'm also going to, well, I'm going to go through the elimination rule, but for the introduction rule, if I wanted to say P or Q is true, what sort of information do I need? Well, so one idea would be, well, what if we manage to prove that P is true, then no matter what, P or Q will always be true, right? It doesn't matter what Q is, I can just sort of introduce a new arbitrary symbol and say, well, P or Q is true. So that sort of gives us this idea for our disjunction introduction, where we can say something like, if I manage to prove that A is true on line N, then on line N, I can say A or B is true. And my reasoning for that is by doing or introduction, right? Because clearly, if one of the disjuncts is true, then the overall disjunction is true. The elimination rule, though, is a little bit yuckier, more yucky. I don't know, whatever is the correct grammar for that. We can't really get anything out of the statement A or B, right? Like, I don't know what the truth value of A is. I don't know what the truth value of B is, but all I know is that at least one of them has to be true. So that gives that sort of, instead, we do proof by cases. So it's a little bit of a yucky rule, but it's very reasonably natural, I guess, in the sense where if I manage to prove that by assuming that one of the disjuncts is true, and I can prove, let's say, some conclusion C, and if I assume that the other disjunct is true, and I can still prove C, well then no matter what choice, whichever one of A or B is true, C must be true, right? C follows from either case. So this is going to be your sort of proof by cases, your natural strategy for getting rid of disjunction. So I guess memorize this rule too. Our next one would be negation. So negation is also kind of interesting. To introduce a negation, what does it mean when we say something's false? Well, if I sort of assume that P is true, and I somehow show that assuming P is true leads to a contradiction, then P obviously cannot be true, right? Because if P was true, well, then my system would be inconsistent, and that's undesirable. So we're going to say that if by assuming A, I can prove false, if I can create a contradiction, then I'm going to go introduce not A with this not introduction. So say not introduction, and I'm going to cite the entire proof. I'm going to say this subproof from M through N tells me that A is a contradiction, so not A must be true. Note, this is not the same as proof by contradiction, because in proof by contradiction, you're assuming not A, and you're claiming that by assuming not A, and then proving false, you get A. That's not true. You get not A. But turning not A into A is what classical logic. Well, you need classical logic axioms for that. That's called double negation elimination, equivalent to the law of excluded middle. As for negation elimination, well, if I have a contradiction, if I manage to somehow prove that not A is true, and I've also managed to somehow prove that A is true, well, then I know something went wrong, right? So I can sort of think of not A as like a function from A to false, or as an implication from A to false. So I can do the modus ponens rule in a sense, and sort of say, okay, well, I can prove false. And why is proving false useful? Because from false, anything follows, right? This is called the principle of explosion. It's basically saying if I can derive a contradiction, then I can just prove anything. So this is why we don't want. This is why we want our systems to be we want our systems to be consistent. We don't want our systems to be inconsistent because then any truth trivially follows. But yeah, so those are our rules for the inference rules that we want to have for a logic system. Here are some examples of proofs that you're going to see in natural deduction. So this one, what does this say? Well, this says, here. Okay, so what this is saying is with the assumption that A implies B, A implies B implies C, I want to derive that A and B implies C. So how do you start a proof like this? Well, you're going to go start with, right, the line, the assumption. I'm going to say as our assumption, well, right here, this is our assumption, right? So A implies B implies C. So we're going to say this on line N1, and somewhere at the bottom, we want to somehow end up with the statement A and B implies C. So I guess your first thought here is you don't actually want to go try to do your proof from top to bottom. You're going to kind of want to bounce back and forth between your hypothesis and your conclusion, and you're going to go want to work both forward and backwards. So if we look at our assumption here, we see A implies B implies C. Well, what can we do with that? our inference rules don't really give us anything we can really do here because, but to get rid of this implication, we need to somehow manage to get a proof of A. And in our assumptions, we don't have anything we can do to get a proof of A immediately. So your first thought should then be, okay, well, what do we have from our conclusion? Our conclusion says A and B imply C. The most upper level connective over here is going to be this implication, right? So what you're going to want to do is you're going to assume I'm going to probably want to end on implication introduction because I want to introduce this this conditional. So if you recall what our implication introduction rule looks like, it says if I assume A and I manage to prove B, then I can say A implies B. So I'm going to go sort of pattern match this into here. What is my assumption? My assumption is going to be this A and B. So I'm going to go start a new subproof. And I'm going to assume A and B. And at the end of this, I'm going to want to end up at my conclusion. What's my conclusion? My conclusion is C, right? So then from here, what can we do? Well, C doesn't really look like we can do anything from C. We just know that we somehow want to get to C. So we're going to ignore this for now. And now we're going to look again at our assumptions. What can we do? This one, we still can't really do anything with. But this one, we can break apart, right? We can get some information from A and B. So I'm going to do that. I'm going to say, well, let's say A is going to be true, and we know B is going to be true. I'm going to say that's by and elimination on line 2, and elimination on line 2. And from here, I can now actually do stuff, right? Because these are the assumptions, these are what I know as of right now. So now that I know A, I can finally use this guy who I've always wanted to use. And I can say, all right, modus ponens. I can use the duplication elimination rule. So to say, okay, well, since I have A and something, and I have A, I can conclude something. So I'm going to conclude B implies C by implication elimination on line 1 and line 3. So that's going to give us this B implies C. What do you think we should do to get rid of this B implies C? I mean, the answer is right there, but we should get rid of this B. To get rid of this B implies C, we want to use the fact that B is true, right? The fact that we've already proved B. So what do we get from that? We get C, which is our desired result. So we can say, okay, by implication elimination on 1, 2, 3, 4, 5, line 5, that's our implication, and line 4, which is our hypothesis, we managed to prove C, and that concludes the proof, because now we've gone through entirely what we want to see. This is something that's very machine checkable, and I hope, as long as you know the rules, reasonably natural to do. But yeah, here's an example of a more complicated proof. Do you guys want to go through this, or do you want to just like kind of skip past it and talk about first order logic? Skip past it? Okay, that's fine. Just sort of make sure you kind of understand how we use these rules to go from one step to the next step. But yeah, so that's great and all, but quantification is very useful, right? We want to say something about, like, it's useful to be able to say stuff about things. So remember, this is our grammar for first order logic. We're going to go add a couple of new axioms. So we'll inherit all of our inference rules. We're going to inherit all of our like inference rules about conjunction, disjunction, implication, and explosion, reiteration, whatever, from propositional logic. But now we're going to go add rules for universal quantification and existential quantification. So the first one here is going to be the universal quantifier. If you think about how you write proofs about universal statements, right? What you always do is, again, you start with let X in A or something. Like if it's for all X, PX, you say let X be arbitrary. And at the end of my proof, I prove PX. And only once I can do that, I can conclude, then therefore for all X, PX. So this universal quantifier deduction rule is going to be similar. It's going to adapt the like exact same sort of idea. And you'll also note it looks similar to implication. There's a reason for that. If you look into dependent type theory, this is actually something called a pi type. But again, not very relevant, but it is relevant if you want to do automated theorem proving. But essentially we say, okay, if I assume that I have some arbitrary A, right, some arbitrary symbol A, and this is going to be like now specialized, I say, and I managed to prove P, well, I have some predicate P of X, substitute a for x in this predicate. So we have something like, my predicate was something like, I don't know, x is prime. We now, this PA over x is going to give me a as prime. So if I manage to assume a and show that a is prime, I can now conclude that for all x, x is prime. Make sense? Reasonable? All right, so this is going to be called for all introduction, or you might hear some people call it for all generalization or universal generalization. The elimination rule is sort of analogous, right? So if I know that for all x, px is true, then given any concrete example of x, so if I know that, for all natural numbers n is greater than equal to 0. If I know that that's true, then you give me a specific natural number, I can tell you 9 is greater than or equal to 0. So this is going to be called for all specialization or for all elimination. And what it's going to do is basically, if I have for all x, px, for all x, x is greater than or equal to 0, then I can say, well, substitute a for x, and I get to claim a is greater than or equal to 0, where a is like a concrete variable. Makes sense. The existential quantifier is analogous, but it goes the other way around, right? So to introduce an existential quantifier, what do I have to do? Well, I have to somehow prove that there's an instance of my predicate that is true, right? If I want to show that there is a prime number greater than 10, I have to give you an actual prime number greater than 10. So I think 11 is prime. So we're going to say, okay, so I get statement 11 is prime, then, or like 11 is a prime number greater than 10, well then I can introduce the statement, there exists an x such that x, so I replace 11 with x, I say x is a prime number greater than 10. Make sense? So it's also supposed to be relatively intuitive, I guess. The elimination rule is also analogous. It's like the reverse, right, of this. Actually, it's very similar to the, it's like the dual of the for all operator, of the for all connective. But here, what we're going to say is, if we know that there exists an x such that px, we can just sort of assume that we know which x it is, but we don't actually know which x it is. We're just going to say, well, suppose that we have some x that's the prime number greater than 11, greater than 1. If I manage to somehow prove something about, let's say, there are lots of prime numbers or something, right? If from the assumption that there is a prime number x that is greater, or prime number a that is greater than 10, if I manage to somehow prove that there are a lot of prime numbers, then I can kind of just get rid of this there exists and show that then therefore I have there are a lot of prime numbers. Note that there are a lot of prime numbers does not depend on my particular choice of a, right? It's just, I just assume that I had some a, I managed to prove something that's not dependent on a, so then I can now assert that that thing that is not dependent on a must be true. So that's the there exists elimination rule. From here, those are really the only rules that we need to add to upgrade our system or extend our system to first order logic. So we have another example. I'm just going to show a proof here. Instead of doing it on the board, I guess we can sort of just talk through what it's doing. But it's basically saying, okay, I assume that for all x, f of x implies g of x. And I assume that there is an x such that f of x, right? So what does this do? This says, I want to kind of open up a subgroup. So there exists an x such that f of x. I'm going to assume that I have that particular x. So I'm going to say, fa must be true, where a is arbitrary, right? Well, not arbitrary, but like a is a concrete thing that I don't know. Well, from here, I now have a being concrete. I can apply the for all rule and say, well, I know that for all x, f of x implies g of x. So surely f of a must imply g of a, right? So I can then say, okay, well, using the for all elimination rule, I've managed to derive for all, or fa implies g of a. Well, I can use the implication elimination rule, and I can now prove GA must be true. And from GA, well, I can now generalize this with that there exists. Since I managed to find the existence of some A for which GA is true, I can now say there exists an X such that GX is true. And then by the existence elimination rule, note that there exists an X such that GX is not dependent in any way on our choice of A. This is a statement that stands by itself. We can then just sort of pull it out of the proof as our result and say, okay, well, there exists an X such that G of X by the existence elimination rule. Sense? Okay, so now suppose we wanted to actually do something useful, right? We want to have, well, I guess it's still not useful, but like more useful than just standard intuitionistic logic. But we want to upgrade to classical logic. So what does that entail? Well, remember, classical logic takes the law of excluded middle, which basically says that for any statement P or for any sentence P, for any proposition P, either P is true or its negation is true. So that's basically assuming, right, that there is a definite truth value. We might not know which truth value it is, but there is a definite truth value. That is this rule over here. It doesn't look like it, but convince yourself that this is just asserting P or not P and then applying the or elimination rule. The reasoning why we have it written this way is because typically it's not really useful to just introduce the statement P or not P. Every time we want to use the law of excluded middle, we typically just want to say, okay, well, we're going to go try cases. Assume that P is true and assume that not P is true. And I managed to prove something independent of my assumption. So then therefore I can say that that thing that was independent of my assumption is true. It turns out this axiom is actually equivalent to another axiom called double negation elimination, which perhaps might be a little more intuitive in the sense where double negation elimination says not P implies not P means P is true. So I can prove that not P is true, that P is true. That's basically bivalence, right? It's saying that we only really have truthity and falsity. Those are the only two states that we can have for truth values. So that you can kind of convince yourself that that's equivalent. There's an exercise where, like in the slides, where there's a solution where you can sort of try yourself and see if you can prove that double negation elimination comes from the law of excluded middle. Also equivalent is the axiom of indirect proof or proof by contradiction, right? So if you recall proof by contradiction, what you do is you always say, I assume not A, and if I can prove a contradiction from assuming not A, then I can say A is true. Again, this is different from the negation introduction rule in the sense where the negation introduction rule from this assumption gives us not A. So you can sort of see how double negation elimination would entail this indirect proof principle. But if you did not have double negation elimination, if you had no way to get rid of that not, then you don't really have a way to assert A. So yeah, these are the three axioms that make your system into a classical logic, and they're all equivalent. The exercise is over here. You get to prove it. You want to prove it, or do you just not care? If you guys don't care, then we can skip them. But if you guys are interested, we can try doing some of them. Okay, you want to take a look at this one. All right. So maybe it'll be helpful if I write all the inference rules down on the board. So because perhaps you guys didn't actually memorize them when I told you to memorize them. So I'm gonna go write out stuff. So I can always say I can reiterate on M. For the AND rule, I want to say if I manage to prove A and I manage to prove B, then I can prove A and B. So this I'm going to say is, let's say MN and introduction of MN. Actually, what do we need for this one? No, we don't need and. Yeah, we don't need and. So I'm going to say, I'm going to give you the ors. So if I have this or introduction on M, I have equivalently Q, M, P, or Q. I have or introduction on line M. What else do I need for this one? Is this enough? No, so I want to also give you not elimination. So I'm going to say, if we have not P and we have P, then we can say false. This is going to be by not elimination on M and N, and I'm going to give you explosion. So if I have false, then I can find P, and that's going to be by not elimination on M, let's say. So I'm going to give you these. So with these, now we want to go say, what do we want to assume? We want to prove double negation elimination. Maybe I should also give you the law of excluded middle. That might be helpful. Well, that is going to be helpful. In fact, you can't do it without it. So I'm gonna say if I have a subproof P and I prove R, subproof not P and I prove R, then I can prove R by law of excluded middle on these guys, I through J, K through L, let's say. So we're going to start with assumption. So I want to go prove double negation elimination, which means I want to prove that not P gives me P. So any idea? What do you think we should do? So what do we know? We know not P. We can't really do anything with not P, right? So what might be an idea for a thing to try? Which one of these rules do you think might be useful? Is it helpful to reiterate? No, exactly. Is it helpful to, well, I guess, forget about the and for now. Is it helpful to introduce an or? Okay, so one question would be, I guess, we know that the law of excluded middle entails, is able to derive double negation elimination. So what is maybe an axiom that we might want to use to get started with? All right, what if we try using the law of excluded middle? Maybe that's a good idea. So I'm going to say, we're going to go assume that P is true, and we're going to also have a subproof where we assume that not P is true, right? That's what we need for the law of excluded middle. Well, if P is true, what can we do? Remember, we want to end up at, we want to end up at P. So if P is true, what do we want to do? Yep, exactly. We're sort of done already, right? We assume that P is true. So it always suffices to just reiterate. So that's going to finish that proof. What if not P is true? I'm going to put parentheses around this. So maybe it's a little more obvious.
Not is true. Let's see. Not is true and not is true, that's gonna be false.
Yep, exactly. We use negation elimination at this part over here. So what happens over here? I can prove bottom. So I say, okay, I managed to prove false by not elimination. On what? Well, I know that not P is true. I also know that not P is true. So I'll say by not elimination on 1 and 4, I can prove bottom. And what do we know from false?
Anything.
Yep, anything comes, right? So we can say P by bottom of elimination on, let's say, line 5. And then this just follows directly from the law of excluded middle, right? By assuming P, we proved R. By assuming not P, we proved R. Therefore, P follows from law of excluded middle with 2 through 3 and 4 through 6. So I think if I forward the slide, not that one, this one, you'll see that sort of is exactly what we just did, right? The next exercise, double negation elimination implies indirect proof. You guys want to do this one? Was that yes or no?
Leave it as an exercise.
All right, leave it as an exercise. Well, the exercise is what you can see the answers on. Oh, that's a big one. You can see the answers on the slides if you want to, if you want to go give them a try. But yeah, any questions?
So has this like been implemented in like any sort of like, and you can talk about like the applications of it, I guess?
Yeah, so this natural deduction systems of this sort are actually, have you heard about proof assistant? Have you heard about proof assistance?
No,
Okay, so there's an idea where we want to sort of have, writing math proofs is hard. It's very often the case where we think we proved something and it turns out there's maybe some sort of logical bug in the proof that we made. We can't actually, well, so how does this? It's difficult to verify that proofs are true sometimes, right? The proof of the finite simple of the classification of finite simple groups is something like 300 pages long. How do you verify that? Who knows? So the idea is, what if we had computers try to verify these proofs for us? The good thing about these sorts of systems is that computers can understand them. So by doing this sort of gives us a computational model, right? You can, okay, I guess we're going to talk about type theory. There's these proof assistants use something called type theory, where essentially you model logical propositions as data types, and then a proof of this proposition is going to be like a term that has that data type. So in a very simplified sense, I might have a data type like there is a prime integer or something, right? And then my proof of that is an actual integer, 3, right? And that's going to be something that has type, there is a prime integer. And by doing that, your computer can sort of verify that your proof is valid. Every single step deductively follows. And then there's a correspondence between these sorts of subproofs you can sort of think of as functions, right? These assumptions are basically saying, well, if I had a proof of P, can I somehow transform it into getting a proof of P? Or like if I had a proof of not P, can I somehow transform it into getting like a value that tells me here's a proof of P, right? So if you can think of these as functions, then you can give a computational semantics to them. And once you can give a computational semantics to them, you can create programming languages that allow you to do these sorts of computations. So that's one big application. Another application is in software verification of, formal verification. So again, as I mentioned earlier, unit tests, they don't really tell you anything, right? They can only tell you when your thing fails, but they can never tell you if your code is correct. What some people do is something called formal verification, where they try to use these sorts of methods to prove properties about their code. So they would have things like, suppose I had this with my function gets called with these assumptions, like the inputs are always going to be non-empty, and so is the case, and it's the n is always going to be greater than 5 and whatever. And I want to go prove that no matter what, as long as my contract is satisfied, I will give you something that is a meaningful result. You can actually, if you can write enough assertions in like logical form statements, you can actually, it's a very tedious process and they're working on automating it, but you can actually have stuff like proving that my function will always give me a Fibonacci number, or my function will always give me non-empty lists or something like that. So now I know for certain my function will never fail. Not that I know maybe on these inputs that I tested on my function will not fail. So those are actual applications. Yeah, they're mainly in programming language stuff is I think where the big applications are, but you also have like linguistics. Linguists like to model grammars as like type theories and models of computation. Proof theory sort of gives you like actually maybe a quote over here from Robert Harper, Carnegie Mellon. There's this thing which I like to call the holy trinity here of computer science. The correspondences between proof theory, which is a theory of logical proofs, algebra and category theory, and then the subject of the computer science side, which are programs or type theory. The idea is that types have proofs have a very close correspondence with types, and types are essentially the same as programs. And these programs have a very close correspondence with categories. We can do categorical semantics for things. So I guess maybe this might be a little too ambitious. No, I don't want to talk about category theory. So we're not gonna talk about those. But the idea is there is a very nice correspondence between, you can translate between things of this form and programs, like mechanically. And you can also translate between programs and these like sorts of algebraic structures called categories. And you can basically just keep going all back and forth in this circle. And it allows you to do a lot of interesting things about like what is computable, philosophical things, as well as also practical things in like the software engineering sphere. Hopefully that's helpful. Anyone else have questions?
So why are we introducing the law of exclusion below, like at the end of this? Does it feel like more unnatural than other theorems?
Yes. So what I'll say is most of the time these natural deduction systems are formulated in these intuitionistic systems without the law of excluded middle. Why? Because once we add the law of excluded middle, the sort of the ability to kind of say that it's either true or not true or something like that, or like let's say proof by contradiction, right? What you end up with is like you lose the computational meaning behind your proof. Each of these proofs without the law of excluded middle are sort of like I'm transforming proofs. Someone gave me a proof of something, I transform it into a proof of another thing. And then I keep doing that chain as like a function kind of pipeline. And then at the end, I get a proof for the result that I want. When you have the law of excluded middle, you sort of allow things like the least upper bound principle in real analysis, which says that every bounded set has a least upper bound, has a supremum, right? What is that supremum? Who knows? I just know that it exists. That breaks our computational semantics because we have no way to actually produce it, right? If I told you I define root 2 as the supremum of the set of rationals where b squared is less than 2 or something like that. Well, that's great. Can't really do anything with that. So I can't really do anything with that computationally. So that's why a lot of computer scientists, just for convenience, like to reject the law of excluded middle. Anything else? But I guess that's it. We're out of time anyway. So yeah, here's some sources. You'll notice if you want to learn more about this, there's stuff from Oregon Programming Languages Summer School 2012 in particular, has a trio of lectures from Robert Harper, who I quoted a couple of times on type theory, Frank Fenning, who is a professor in CSM philosophy, and he does some stuff on proof theory, and then Steve Audi, who does some stuff on category theory, and all their lectures are kind of like tied within each other. So if you want to kind of have like a, what you would call it, if you kind of want to have if you want to learn more about this, that's a good resource. CMU in general is a good resource for this sort of thing. And then I think University of Washington, University of Pennsylvania, and San Diego also have some very nice stuff on here. So yeah, thanks.